I'm just going to record this. So we're going to finish work energy power today. Can I just ask for a show of hands, how many of you have got your booklet 2, the chemistry booklet here? Just let's see. Okay, so that's virtually everybody. I don't know about you, but I'm getting a little bit tired of physics, so I'm hoping to do some chemistry after we finish work energy power. Then we can go back to physics, and then we're going to probably do momentum. But let's just finish off our work energy power. Now, you know, last time I couldn't see you, so I think I was like a fool and a madman. I was just talking to myself. I went on for about an hour and 25 minutes, and I think you guys had left me long ago. But anyway, the video is there on YouTube, and we went through that booklet, and we finished all the questions on work energy and power, those short questions. Okay, so let's just have a look at one long question from last year. Now, you guys know where to get the last year's questions. You just Google WCED, Western Cape Education Department, past papers, grade 12 physics. And then this is what comes up. You get past papers. Okay, so I take it you can see there's question 5. Okay, so this is a long question. So we must do some short questions, we must do some long questions. Question 5, an object of mass 1.8 kilograms slides down a rough, okay, there you can see they've drawn it rough, curved track and passes point A, which is 1.5 meters, there they show it above the ground, at a speed of 0.95 meters per second. Whew. The object reaches point B at the bottom of the track at a speed of 4 meters per second. So, what are the questions? Okay, define the term conservative force. Okay, so, so for 2 marks, what is a conservative force as opposed to a non-conservative force? Well, it's got something, who thinks they know the answer to what is a conservative force? Just a kind of like a rough idea of what's a conservative force. Anyone give me an example of a conservative force? Okay, so the force of gravity, where it doesn't matter about the direction that it doesn't matter about the path the force takes, that is a conservative force. So electrostatic force, gravitational force, a force where the pathway doesn't matter. Now, guys, as you know, I might think, yeah, this looks easy. It always helps to go to the memo. So we'll have a look. That'll be our tentative. That's our answer. Then we'll just have a look at the memo. Okay, name the conservative force acting on the object. Okay, so what force is acting on this object? Okay, would it be electrostatic? What would it be? Friction? Is friction a conservative force? Hands up. Would it be gravity acting on that? Hands up. Okay, so it's gravity. There's your conservative force. Okay, gravity is pulling it down. So force of gravity or weight. Is mechanical energy conserved as the object slides from point A to point B? Choose from yes or no. Give a reason for your answer. Okay, so look. What's the law? Mechanical energy is always conserved. That means the sum of your kinetic and potential energy is conserved, unless there is a non-conservative force, like friction. So is there friction between A and B? Who says there's friction between A and B? Hands up. What's that rough patch there? Yeah, great, thank you. Appreciate your participation. Okay. So is the mechanical energy conserved? And the answer is no, because the friction steals some of it. Okay, so it's going to not have the same mechanical energy as when it gets to the bottom. So the reason friction is going to steal some mechanical energy, the non-conservative force is going to steal from the conservative force. Calculate the gravitational potential energy of the object when it was at point A. Okay, what is the formula? mgh. That's So easy peasy. I just go mgh, mass 1.8, g 9.8, h 1.5, and I get my answer. Hey, I'm feeling like a genius here. I've got 3 marks, I've got 2 marks, I've got 1 mark, I've got 2 marks, okay. Using energy principles, calculate the work done by friction on the object as it slides from point A to point B. So, okay, so that's about the only challenging thing here. So who's going to tell me, do we have a formula for work done by friction? Who thinks on your BFF there's a formula for work done by friction? Any ideas? Anyone know a formula? Hands up. Anyone heard of a formula? WNC? Anyone heard of WNC? Okay, so here's the formula. WNC equals change of kinetic plus change of potential. So I go to my BFF and I get and I know that that's the formula I'm going to use. Okay, so what is the change of kinetic? There's its speed final, so I'm going to say its kinetic energy at the bottom is half mass times velocity squared. There's its kinetic at the top, and I'm going to take the final minus the initial kinetic, and that's the change of kinetic. And here's its potential at the top, and it's got no potential energy at the bottom, so it's 0 minus whatever our answer in 4 was. And then we add those, and we get the sum of our mechanical energy at the top. That's the potential kinetic at the top. And then we get the sum of our kinetic potential at the bottom. The difference is going to be the frictional energy. So it's going to be that formula, WNC. Calculate the gravitational potential energy of the object when it was at point A using energy principle. So we're going to use the formula here. Let's just see. Where is my, I've got a thingy to, what am I? I'm working in, oh, I'm working on, I can't draw on it because I'm working on a different program. Okay, so the formula I'm going to use is WNC equals change of mechanical energy or kinetic energy, change of kinetic plus change of potential. Can you guys do that? I mean, it's just really straightforward, but I just want you, hands up, can you do it? And will you do it? Can I ask you to do it for homework or at the end of this lesson? Is that a thumbs up? Thumbs up? Yes. Can you do it? Do you want me to explain it again, what we did? Anyone want us to explain it again, hands up, or can you all do it? I don't see any hands wanting to explain it again. Okay. Is there someone? Okay, so what are you going to do? I'll just do it again. You know how to work out kinetic energy from that velocity, half mv squared. You know how to work out potential energy from that height. You add the two energies at the top. At the bottom, it's got no potential. It's only got that half m times 4 squared at the bottom. So, as I say, I can't draw on this. That's actually just a slight problem. So I can't, but I could virtually do it almost mental arithmetic. A half times m, which is 1.8 times 9.8 squared, is going to give me the kinetic energy there. And then the potential energy, mgh there. I add that. Then I work out the total mechanical energy at the bottom. It's got no potential. It's only got kinetic. And then whatever the difference is, or that is the answer. That is what work non-conservative was. That went into friction. Okay. So please try and do it. And then it says surface BC in the diagram above is friction, BC. What is the value of the network done on the object as it slides from point B to point C? Okay, now you've got another formula for network. Network is change of kinetic energy. Now this is frictionless. It's traveling at 4 meters per second. Who thinks they know what the speed will be at C? Hands up. on a frictionless surface. Who thinks they know what that answer will be? Let me give you some choices. Will it be less than 4? Hands up. Will it be equal to 4? Hands up. Will it be greater than 4? Hands up. Guys, I'm getting worried. I'm feeling like a madman. Just, if you have no friction, what's there to change the speed? It's going to stay 4. It'll stay 4 forever on a straight flat surface. Okay, so there's no work done on it. There's no friction, there's no gravity, nothing. So we use our work energy theorem, which says work net equals change of kinetic energy. And there's no change of kinetic energy, there's no change of velocity. So there's no net work done on it. And that's for 1 mark. And there we apply our work energy theorem. Let me just see if I can, how do I get back to Zoom? How do I get back to where we were? Let me just see if this works. Can you guys see the memo for this?
Guys, you need to see.
Can you guys see the memo? Or can you just see me?
You can see the memo, sir.
Fantastic, thank you. Okay, it was question 5. A conservative force is a force for which the work done in moving an object between 2 points is independent of the path taken. I think we said something like that. A conservative force is a force in which the work done, okay, that's underlined, is independent of the path taken. So that's a force like gravity or electrostatics. Then there's our answer, gravitational force. Now, the question 5.3. No, there is friction. That was what stopped the mechanical energy from being the same top and bottom. There is a friction or non-conservative work. And then I see they add here, it is not an isolated system. What they mean by that is there's something that is changing the mechanical energy. If it was just mechanical energy, I guess I would call that an isolated system. Then 5.4, there's how we work out the potential energy. EP equals mgh, 1,8 times 9,8 times 1.5. So that is how much potential energy we have at the top. Then 5.5, we had work non-conservative equals delta K plus delta U. This was the formula. So we plug in our, I see, look what they do. They put a bracket there. Half M, and then V final minus V initial squared plus mg, H final minus H initial. And then they get the amount of non-conservative work or energy done was that. So there's the formula. There you're working out kinetic final minus kinetic initial plus potential final minus potential initial. Get the difference. And there, look, it's a negative 12,87. Work NC is always negative. And then the work net is 0. They didn't ask us for a reason. Okay, so you can also Google, it's a very good idea to Google the memo. Now let me just see how do I get back just to, okay, yeah, let's stop share. There we go, now we're back. Okay, any questions? Anything else that you guys would like to ask on this work energy theorem? Sorry, were some of you copying that down? Do you want me to go back there? Who wants to go back there? Look, I think it'll be better if you just try and work it out, as long as you know how to do it. Are we good with that? Okay. If it's okay. Yeah. If it's okay with you, can we go on to chemistry? Okay, booklet 2. Thank you. Now, what I thought we will do in booklet 2 is the last time we did chemistry, we did the naming of the substances. Now, there's a section on addition, elimination, and substitution, which kind of follows on the naming of the substances. So let us do the questions that relate to that. Okay, so I'm going to go back to sharing, and I'm going to go to preview to the booklet. Okay, let's go to question 1.6. Well, hang on. Let's just quickly revise it. Okay. Do you remember what addition was? Addition was when you had a double bonded something or other. When you had something that was double bonded, like you had a C double bond C, and then it went to form C single bond C. And that is known as addition. Okay, do you remember that? That's addition. Then elimination is when you go from C, single bond C, goes to form C double bond C, and that is known as elimination. And the last thing we had was where you go from C, single bond C, goes to C, single bond, hey, I should put the caps on. C goes to form C, single bond C, and that is known as substitution. So there are the three possibilities: addition, elimination, substitution. Now, I seem to have lost you, but I'm sure you will come back to me. I'm sure all shall be well in the end. Okay, so I'm not sure if you can see me or if the whole thing bombed out. Let's just go back there. Let me stop screen share. There's still 2 participants, but I just can't see you. Maybe there's just something that went wrong there. But anyway, I'm going back to where we were. Okay. So I'm just going to presume you're there. I can't even see me anymore. Okay, when 2-chlorobutane is strongly heated in the presence of concentrated sodium hydroxide, the major product formed is, okay, so 2-chlorobutane, we're going to go methane, ethane, propane, butane, so we know butane is 4. We look at it, it's an ane, so it's single bonded. And if we're going to add sodium hydroxide, let me just draw this for you. 2-chlorobutane. Let me try my best to draw that for you. So it's going to be C, single C, single C, single C, single. And on carbon number 2, it's going to have a chlorine. Okay, so let's draw a chlorine. Cl. Whoops, not C capital L. C little l. Okay, I lost you there for a moment.
Yeah.
But can you still see and hear everything here?
Sounds a bit better than it was. Sir, they were having problems before. It was very broken.
Oh, the sound was a bit broken.
Yes, yes.
Okay.
But it's fine now.
Let me try and say that again. How do you recognize addition reactions? It's when a double bonded carbon goes to single bonds. By breaking those double bonds, you've got to add two substances to it. That's addition. Now, when you go from single bond, we call that saturated, to carbon double bond, we've got to get rid of two hydrogens or something, and that is called elimination to then form the double bond between the two carbons. But now, how do we recognize substitution? Substitution starts with a single bond, ends with a single bond. Okay, so I can't really draw it perfectly here, but there is 2-chlorobutane, methane, ethane, propane, butane, and on carbon number 2 is chlorine. Now let's suppose then that we add NaOH. Okay. Now guys, you know about chemistry. Let me tell you what I see when I see this. Let's see if you can begin to see with my eyes. When I look at chlorine, I see a very sexy girl. Very. She's at the bottom of the redox table. And when I look at sodium, I see a very sexy guy. Okay, so chlorine is dating butane, and sodium is dating hydroxide. So you've got like an 8 dating a 5, and you've got like an 8 dating an 8 guy dating a 5. OH is a negative, is like a girl. So that's how I'm looking at it. I'm seeing chemistry here. Now this is what I'm seeing. I'm then seeing that the two hotties, that's sodium, are going to join together. Okay, because there's no faithfulness in chemistry. The ones that are, the two hotties will just grab each other. Very hot. Why would sodium stick around OH? Why would an 8 stick around a 5 when an 8 can have another 8? And why would this chlorine stay on butane when it can have another 8? So then we know that what is going to be formed is going to be NaOH. Oh, where's the text in here? Come on. NaCl, Cl is going to be formed. Okay, should be a capital Na. So NaCl, Na is going to get on with Cl. Now there you got two 8s. Why are they 8s? Because they're high and low on the table. So that leaves us with what's left. We know that OH is now left, OH is just left by itself. So what is OH going to do? It's going to go and join where the chlorine broke. So now we've got OH attached to the second carbon because the chlorine went off with sodium, and these are the hot couple, and now we've got the not so hot couple. And what is the major product formed? Okay, so you can see it. It's going to be OH on carbon number 2. So butane 2-ol. See how easy that was? Butane 2-ol must be the major product. Okay, what is the minor product formed? Sodium chloride. Okay, I hope that was easy enough. Who thinks that's easy? Hands up. Who understands that? Who thinks this is really... These questions are easy. I'm just going to destroy them, or maybe I'll take them prisoner if I'm feeling in a good mood. Okay, very easy question. Let's have a look. Each paper has got these type of questions. Okay, so let's look for the one. Okay, let's try this one. Consider the reaction presented by the equation below. CH3, CH, CH2 plus H2 goes to form CH3, CH2, CH3. Okay. Now, whenever I see just a single H there, and even I could count them up, 3 hydrogens, 4, 5, 6 hydrogens. So the formula for this is CnH2n. Now, what type of thing is this? Because there's 3 carbons and there's 3, 4, 5, 6. So it's going to be CnH2n. So what kind of substance is this? Is it saturated? Hands up. Who says it's saturated? Who says that's an unsaturated compound? Any hands? Thank you. My genius is there. Okay, from the formula, I know this is unsaturated, and in fact, it must be an alkene. And it's adding a hydrogen. So this must be what type of reaction? Addition. And if it's adding hydrogen, addition, hydrogenation. And then it's going to form an alkane. So this reaction is an example of not hydration, that's water, not dehydration, that's taking away water. It's not substitution because we start with double bonds, we end with single. And there, hydrogenation. I kicked it. I hope you can see that. Okay, so you see how easy that was. Okay, so let's go to the next paper that should have an example of this type of thing. Okay, 1.2.3. The addition of hydrogen to an alkene is known as, well, look, you're adding something to an alkene. Obviously, the alkene is going to break its bonds. That's the double bonds. And you're adding hydrogen. So what is it? Hydration would be adding water. Cracking would be turning a big thing into a small thing. Hydrogenation, adding hydrogen. Dehydrogenation, that would be if you were taking hydrogen away. So the answer is obviously C. I hope you're feeling as smart as I am, how easy those are. And these questions, by the way, are not easy normally. But you should really do some kicking there. Okay, let's look for the next one. So they normally have it, there's a C here. I don't see any so far, yeah? Okay, here. Which one of the following is a product formed during the hydrolysis of bromo ethane? Okay, now guys, write it down. Hydrolysis only occurs during a substitution reaction because it's hydration or dehydration during the others. Hydrolysis is normally when you add sodium hydroxide to something, bromoethane. So it goes methane, ethane, and bromoethane has got one bromine on. So what is the reaction that's going to occur here? So you're going to get, probably they're going to take sodium hydroxide. There again, there's your hottie, Na. Plus bromoethane is going to be methane, ethane. It's going to be carbon with a, okay, let's just try and see if we can draw it. Yeah, going to be here's C double bond C. And there's a plus here. Okay, and on this carbon is bromine. Br. You know something, I'm lying here. This is bromo ethane. It's also, sorry, it's a single bond here. Let's just see if I can modify that. Bromo ethane. It's a single bond. That's just what I was saying to you. Okay. So have a look here. Again, I am seeing chemistry. It's like I see girls and boys here. I see again a very hot guy with a not so hot OH. I see a very hot girl with a not so hot ethane. So what happens? Bromine, which is again low down on your redox table, that's probably a 9 girl, is dating a 5 guy, and an 8 guy is dating a 5 there. Non-metal, okay? If you don't want to be sexist, you could say an 8 metal is dating a 5 non-metal. So what is the obvious thing that's going to happen? Na and Br are going to get together, and they're going to form sodium bromide. And then you're going to have your OH is going to join where the bromine came off. So let's see, which one of the following is a product formed during the hydrolysis of bromo ethane? Okay, is ethanol formed? Is water formed? No, sodium and bromide. Sodium bromide is formed. Is ethene formed? No, that would be a elimination reaction. Is ethanol formed? Yeah, there's your ethanol. That OH is going to join on there, so it must be ethanol. And guys, I want you to please make a note of it. Substitution reactions are the only place where you find hydrolysis, and normally it's sodium hydroxides involved and alcohols are definitely involved. So 3 words linked together in your brain: substitution, hydrolysis, alcohol, and possibly a 4th word, some hydroxide. Okay, so C, easy enough, I hope. Okay, 1.44. Which one of the following compounds will react with sodium hydroxide? Ah, my old friend sodium hydroxide. A hottie with a nottie. In a neutralized reaction. Okay, sorry, I got all excited for nothing. But yeah, this looks like it could be. What is this? Which one of the following compounds will react with sodium hydroxide in a neutralization reaction? Okay, but it's, what are we looking for? We're looking for who says it's A? That looks like it's an aldehyde there. Who says it's B? That's a carboxylic acid there. Who says it's C? That's a ketone with an O in the middle. Who says it's with alcohol? There's an OH on there. Okay, it's obviously B, because look, COOH is an acid. There's an acid with a base is going to form salt and water. So the answer is B. It's not quite addition, elimination, substitution, but it's, hey, let's just do it. So what are you looking for? Look for an acid that will react with a base, because they said it's a neutralization reaction. Okay, we don't want to do acids and bases at the moment. I'm just looking for this type of ones with how you turn from one thing to another. Okay, I like 1.58. Now this is how the long questions normally look. In the flow diagram below, P and Q represent 2 organic compounds. So look at that. Double bond, add hydrogen bromide, and you get P. Then add sodium hydroxide, and then you get another thing. So what are you guys seeing is happening? what kind of reaction is happening when you've got a double bond and you're adding H and Br? Okay, hands up. Tell me this. Is it a addition reaction? Who says it's an addition reaction? Yes, my genius on the front. Ezra, is that you? I'm sorry, the screen's a little bit smaller. Okay, Ezra, I think it is. Okay, so we're adding hydrogen bromide. So now what is the name of the substance? It's going to be 1-bromo ethane is going to be here. 1-bromo ethane is P. Now we add NaOH to 1. The bromine is now added on here. We add the sodium hydroxide. And again, this is exactly what I told you. There's the hottie. There's the hottie. Sodium and bromine are going to go together to form sodium bromide. And we're going to be left with OH attached to that original molecule. So it's going to be an alcohol that is going to be formed there. Let's see if any of these is an alcohol. Oh yeah, look, there's an alcohol. OH, anything that ends in OH, so the answer's got to be D. Look, none of the other have got an O in them. So we added bromine, then in this substitution reaction called hydrolysis, we took off the bromine and we ended with an alcohol. Remember what I said to you 5 minutes ago? Substitution is associated with sodium hydroxide, alcohol, substitution. And obviously there's heat and other conditions required. Okay, I hope you're getting the idea of this. You know, I'm always kind of scared of this type of stuff because there's memory work involved. Okay, let's just have a look at this. And memory work, you know, you guys have got great fresh minds, but I'm not complaining about my brain. My brain is, let me say, nothing bad about me. There's enough people who do. What product will be formed when an alkene reacts with water vapor in the presence of an acid catalyst? Wow. Okay, alkene plus water will form what? Will it form an ester? Will it form an alkane? Okay, so here's what's going to happen. I can see this. Alkene is, let's take the simplest alkene. C, double bond C, plus H2O is going to form what? There's our alkene plus H2O. Break the double bonds. The 1H is going to go there, and the OH is going to go there. So we're going to get an alcohol. That looks logical. So the answer must be C. And that is an addition hydration reaction. Okay, addition hydration. How do we know it's addition? Because we go from double bond to single bond, and it's going, there's the alcohol it's going to be formed. In this case, it would be ethanol. And it's addition because we're adding water. Hydration, that's the type of addition when you add water. And what's formed? The OH is on one of the carbons. Okay, yay, here's a double, they give us more. 1.6, which one of the following represents a substitution reaction? Okay, what did I say about substitution? Normally there's something that's got a, well, let's just have a look. There's different types of substitutions. Okay, the first thing I know, I can eliminate A and B because they've got double bonds. I can eliminate C because it's got a double bond. And here I go to this one. It starts with single bonds, ends with single bonds. I don't even have to stress my brain. It must be B. How else do I know it's substitution? I start with 1, 2 compounds and I end with 1, 2 compounds. If you look at these, you start with 1, 2 reactants, you end with 1 product. Look at this one. You start with 1, 2 reactants, you end with 1 product. So when you start with 2 and you end with 1, that's called addition. Here's you start with 2, you end with 1. Sorry, you start with 1, you end with 2. That must be elimination because it started with 1 and it eliminated the water. But when you start with 2 and you end with 2, it's substitution. Okay, so now there's 6 things you got to remember for substitution. Normally there's a bromine or whatever involved. There's an alcohol involved, and there's single bonds involved, and yeah, well, I think that's enough. It's like easy enough. I hope you find it easy. And you know what? If you didn't find it easy, go and look through it. See if what you don't understand. And then that's what we got WhatsApp for, to ask questions. Consider the reaction represented below. C3, H2, 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 C3. Okay, that's obviously an alkane. Goes to form C3, CH. When I see an H by itself, there's a double bond, CH2 plus X. So what did I just say? We start with one thing, we end with 2. This must be an elimination reaction, or it could be cracking maybe. But look, it's gone to form a double bond. There's a double bond when you see just... So what type of thing is this? It must be an elimination reaction when you go from 1 to 2. So it's either A or B. And what is product X? So we got 1 carbon, 1 carbon, 1 carbon. That's 3. Here we got 1, 2, 3, 4, 5 carbons. And there we got 3 carbons. So it's got obviously going to be either ethane or ethene because it's 2 carbons. So let's count up the hydrogens. This has got 3 hydrogens, 4, 5, 6 hydrogens. And here we got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this one here has got 6 hydrogens. Okay, 6 hydrogens. Okay, well, let's not try that. Okay, so if it's C2H6, what is C2H6? Is it ethane or ethene? C2H6. Who says it's ethane? Hands up. Yay! Someone knows there. If it was ethene, it would be C2H4. CnH2n, if you like. Okay, so it's A, 174. Okay, a solution has a pH. No, we don't want to do acids and bases. We just want to do this section. I want to get you so into it. Which one of the following organic reactions will take place only when exposed to light? Now you see, this is where I start to think, this is where it's going to start kicking me. Because this is where you've got to go to page 110 of your textbook and learn which of those needs light energy. But let's take a guess. C2H2, that's ethene plus hydrogen goes to form ethane. That one is an elimination reaction, going to take a lot more energy than just light. That one definitely could occur in light. And then this one plus that could go to form that. No, that's a substitution. So it's not D. It's either B. Sorry, it's not B either because that would take too much energy. So it's either A or C. Guys, you've got to go to page 110 on your book. 110, and it says, well, I think we're going to need more than that. But I have a feeling it's this one. So this is where you've got to go and look for the reaction conditions. I think it's this one, but you've got to read that section around about 110, and then you just got to remember the conditions. Write all the conditions under which things occur. But I vaguely remember when you take ethene and bromine, water, you add the two, you've got to put it in sunlight and you get that. So if I were to guess, I would say it's probably that. But I'll put a question mark and you can just check it. Okay, doesn't like the question mark. Go to page 110, look for a reaction, and it's normally an addition of, say, a halogen takes a little bit of sunlight. If you try to add hydrogen to it, you've got to go and look up what is the conditions required for halogenation there or hydrogenation. I don't remember. If I was writing the exam, I'd go and remember them all. I would start now remembering them all. But I don't feel guilty that I don't bother to remember them, because I hope you know, you've got to go, just go and remember the reaction conditions. So we've done that one. It's pure memory work. And if I was writing the exam, gee, I'd be so fastidious about going and memorizing stuff. Okay, the type of reaction that takes place when a carboxylic acid and an alcohol react in the presence of an acid. Now you did this experiment. Who says it's A? Who says it's B? Who says it's C? Who says it's D? A, B, C, or D? Do you remember you did all prac in the first term? You wrote tons and tons on it. You took acids, you took alcohols, and you made an ester, esterification. So the making of an ester is called esterification. Okay, when ethene reacts with hydrogen gas in the presence of a catalyst, the product is, okay, so ethene, double bond, plus hydrogen gas, it's going to be a hydrogenation addition reaction. And then what is it going to form? Ethane. Looks simple enough. Yay. So it's ethene plus hydrogen forms ethane. Addition, hydrogenation reaction. Very straightforward there. Doesn't look like they've got in this paper any questions. No problem. We'll go on to the next paper. Nothing there. Still nothing. I don't see anything there. Okay, well, we've done them all then. And that was painless enough. Any questions? Okay. Who found that painful? Mustafa, did you find that painful? Yes, I expected your hand up. Mustafa, will you go home and study it? Will you get them right now? Asia, how did you find that? Was that easy enough? I can see you there. Will you be able to go home and study them? Will you get them right if I had to ask you them tomorrow or the next day? And Pascal, how was it? Did you find that easy? Jared, I know that you found that easy, right? Was it easy enough? Okay. Mustafa, so do you think when I ask you them again, you're going to find them easy? Did you understand the explanations of why the answers were such as they were?
Somewhat, somewhat.
Some of it. But Mustafa, you know where I live, right? So you can just WhatsApp me. If you mustn't live with your problems. You must overcome your problems. And I'm here to help you. It's like what the Americans say when they go into Iraq. I'm here to help you. Okay, well, seeing as we were so efficient with that, just have a look at this. Let me just see if I can find it. Wait. I can't find it here. Sorry. Let me just go here. Wait, I want to go back. Okay, once more. Okay, take a guess what we're going to be doing next then. Okay, guys, let's just go, if you don't mind, onto then back to booklet one. We're going to do momentum. Okay, let me just see. Yeah, we still got some time. Okay, we've got to make use of all the time we've got together. Okay, so back to booklet one. I've now cured my tiredness for physics. I'm not tired of chemistry. So let's have a look at the physics booklet. Okay. So you remember that song, M1, VR1, M2, VR2, big kaboom and much ado, M1, VF1, M2, VF2, momentum conserved, nothing new. Okay, so that formula is not on your data sheet. The only formula on your data sheet is momentum equals mass times velocity. Now look at this one. Impulse or change of momentum is equal to force times time. They normally write it like this: delta P equals, no, they don't write, where do they write? This is not, they don't use a thing called impulse. They use that, delta P equals force times time. Notice the vector little arrows they put in this booklet. Then if you scramble that formula, force is delta P upon delta T. So impulse is delta P, and so there's a variation of that formula. Okay, let me ask you something. Who can tell me what anything divided by time is called? Anything divided by time is called what? When you see a time at the bottom, it's rate of change of momentum. Rate of. Anything that's got T as the denominator is rate of. So I think they're going to ask in our, in these questions, they're going to say to you, rate of change of momentum is also known as, then the answer is going to be force net. And then here is the law of conservation of linear momentum. In an isolated system, what is an isolated system? An isolated or closed system in physics is a system on which the resultant or net external force is zero. Guys, you've got to remember that, definition. An isolated or closed system in physics is a system on which the resultant or net external force is zero. There's no external force. Anyone remember that problem on, do you remember that problem on change of work as that block slid down the slope? Remember there was an external force of friction. So that's why they said the external force was not zero. It wasn't an isolated system because there was an external force of friction. That was going back to that work energy power problem we did an hour ago, which I'm sure you haven't forgotten. Okay, so with these, only with these few formulae involved, here's another formula. The sum of P before is the total momentum before the collision. There should be a P there. And the sum of P after is the total momentum after the collision. So let's go and see. I have a feeling this section is going to humiliate us. Well, I think it might humiliate me. So I need a bit of humility now and then. Okay, so let's do anything that looks like it's related to momentum and this. Okay, let's just do this one. Which one of the following physical quantities is a measure of the inertia of a body? Okay, which of these is most likely to be a measure of inertia? Inertia is the thing that wants to stop motion or keep you going. So inertia is normally what stops an object from just prevents it from moving. So anyone think it's mass? Would inertia and mass be the same thing? Would a guy with a lot of mass have a lot of inertia? And the answer is yes. Inertia is the one. Inertia and mass are the same thing. Okay, let's look for momentum problems here. An object of mass m is moving at a velocity v, collides head-on with an object of mass 2m moving in the opposite direction at velocity v. So they're both moving at the same velocity, but this is twice as big. Immediately after the collision, the smaller mass moves at a velocity v in the opposite direction, and the larger mass is brought to rest. Okay, so that is the normal rule. If you've got a small thing hitting a big thing, things normally end up going in the direction of the big thing. So then this one bounces off the big thing, and the big thing is stopped. Okay, which one of the following is correct? Is momentum conserved? Is mechanical energy conserved? Okay, who says in every momentum problem, momentum is conserved? Hands up. Anyone? Is momentum always conserved? Yes, it's the law of conservation of momentum. So I know it's either A or C. Now, is mechanical energy conserved? In other words, is its velocity conserved? Okay, look at that. This had velocity v, that had velocity v. This is stopped, that's got reverse velocity v. So I know that if I add the kinetic energy before, it's a lot bigger than the kinetic energy after, because we had at least a half mv squared there plus a half 2mv squared there. They scalar quantity. That's a lot of kinetic energy, a little kinetic energy. So the kinetic energy was not conserved. So what is our answer? It's conserved and not conserved. So the answer must be C. Okay, who doesn't get that? Who does not get what I've just said to you? Okay, so every problem from now on, momentum is conserved, but mechanical energy is only conserved in an elastic collision. And that is when the two objects are of the same mass, by the way. Okay, let's look for a momentum problem here. Okay, 114. Two bodies undergo an inelastic collision. Inelastic means momentum is not conserved. But momentum is always conserved. So we know that the answer is either that one or that one. But if it's inelastic, it means the kinetic energy is not conserved. So there it has to be B. The only time kinetic energy is conserved is in an elastic collision. And that's when the two balls have the same mass. Okay, let's look. Here's in a momentum decision, collision thing. 1.24. During a collision, an inflated airbag in a car decreases the net force that would have acted on the driver of the car. This is because the time interval over which the net force acts on the driver for the same momentum change is 0. The net force on the driver. Is the net force on the driver reduced, increased, or the same with an airbag? This is because the time interval over which the net force acts on the driver. Okay, so does an airbag increase the time or decrease it or keep it the same? Who knows if the answer is A? Hands up. B. C. D. Okay, guys, remember when you dropped eggs off the balcony? What did you want to do? You wanted to increase the time, decreases the change of momentum. We use the formula delta P equals force times T. So if we increase the time, we decrease the force. Time and force are, remember we said, inversely proportional. If you've got force and time on the same side of an equal sign, that means their relation is inverse. So we increase the time to decrease the force. Okay, so I hope that makes sense. Let's just see if there's a momentum. Now, normally everyone's got a momentum problem, but I don't see one here. Nope. Next question. Okay, here's airbags again. Remember, go back to, I forget what that teacher's name was. You could probably remember his name, Mr. whatever. And he dropped his egg from the top of the parachute. You also guys did it. Airbags in modern cars provide more safety during an accident. The statements below are made by a learner to explain how airbags can ensure better safety in a collision. The time of the impact increases. Okay, that sounds right. The impact force decreases. The impulse increases. The change of momentum increases. No, you've got the same momentum. It goes from whatever it's falling at to, you can't change the amount of impulse. If it's falling at a certain speed, or the person's going at a certain speed, they've still got to come to rest. So the impulse, the change of momentum doesn't change. So it's got to be 1 and 2. 1 and 2. Let's see if any of these are 1 and 2 only. Okay, it's D. I wonder why we haven't got these answered. Oh, we must have done them on a different program. Okay, because I remember we did answer that one. Okay, which one of the following statements is always true of inelastic collisions? That's the ones where kinetic energy is not conserved. Both momentum and kinetic energy are conserved. No, both inelastic. Both momentum and kinetic energy are not conserved. No, because momentum is always conserved. Momentum is conserved, but kinetic energy is not. Okay, it must be C. That's true for inelastic collision. Okay, that's Doppler. Now, I don't see any question here on... Okay, here's one. A person drops a glass bottle onto a concrete floor from a certain height and the bottle breaks. The person then drops a second identical glass bottle from the same height onto a thick woolen carpet. That's exactly what you guys did. You, in fact, surrounded your eggs with woolen carpets, but the bottle does not break. Okay, which one of the following is correct for the second bottle compared to the first bottle for the same momentum change? Remember the same momentum change. They both were going at the same speed before, and they both ended up with 0. So the average force on the second bottle was obviously smaller. The time must have been larger. That's how you get the force to be smaller. They're inverse quantities from what we've explained. So the answer has to be D. Okay, let's just have a look at this one. The net work required to move an object is equal to the... I have a feeling this one's going to get me. Maybe you guys can help me out. Net work to stop a moving object is equal to the inertia of the object, change in kinetic of, change in momentum, change in impulse. Okay, how are we going to solve this problem? I think I know we're going to have to use formulae like work net equals delta EK. I wonder if that would help. Using the work energy theorem. Net work to stop a moving object is equal to the change in kinetic work net equals change in kinetic energy. Okay, it must be that one. That is the work energy theorem. Okay, it's not momentum, but I'm not sure we did this one. I know we did this one before. I know we did that one before. But momentum's always conserved, kinetic energy is not in this case. So here the momentum's conserved, the kinetic energy is not. That would be probably, they like to mix that up a little bit. Okay. That's not momentum. Okay, here's a momentum problem. 104. Learners perform an experiment using identical trolleys, each of mass m. The trolleys are arranged as shown in the diagram below. They are initially at rest on a frictionless surface that are connected with a compressed massless spring. There's 2m, there's m. When the spring is released, it falls vertically down and the single trolley moves with a momentum p to the left. The magnitude of the momentum of the two trolleys moving to the right will be. Okay. So we start with no momentum because momentum is mass times velocity. We start with no momentum and we end with going to the left. We have p amount of momentum. Come on, the text. Select text. Oh, okay. P. I'm being stupid. So the amount of momentum is p. To the left. So remember, we start with naught. Now we got p at the end, p to the left. How much momentum do we have to the right here? Let's have a look. 2p, p, half a p, or a quarter of a p. And remember, they're saying the magnitude, they don't care about the sign. Okay, who says it's A, 2p? Who says it's BP? Any hands? Okay, that's the answer. Now let's see why. If you take the momentum before, it's naught. If you take the momentum after, it's got to be the same. So if that has also got P, but it's P to the right, plus P minus P is still naught. So both of those trolleys have got to have a combined momentum of P to the right to match the P to the left. So the momentum before was naught. The momentum afterwards is plus P minus P. And so that has to be B. So even though the masses are different, the velocities will be less. So the mass times velocity will be double the mass times half the velocity will still be equal to mass times velocity after. I hope that makes sense. Okay, yeah, a pendulum bob is released. We did this one. So here comes, we did this one before. There's the conservation of mechanical energy, and then when that hits that, there's the conservation of momentum. And so that's the law we use. We use conservation of mechanical energy followed by the conservation of linear momentum. The answer must have been A. Okay, that's got momentum in it. I don't know if we did this one. The net or resultant force acting on an object is equal to the something of the object in the direction of the force. Oh yeah, I remember this one caught me last time. I hope you guys can see this. I hope that you can see it. Just let me check this. Yeah, there's still 2 participants. I hope you're still there. Okay, so let's just go back to share screen. Back to preview. Okay. So, wait, I've lost you. There's only 1 participant now. Okay, but anyway, I'm just going to continue talking. Maybe you guys will come back. Oh, there are 2 participants. Okay. Share screen. Okay, I trust you guys are still there. Let's go to this question. Okay, this question I know caught me the other day. So we've got force times time is delta P. So if I rearrange that, net force is going to be equal to force net going to be equal to delta P upon T. Okay. So force net is delta P upon T. Change of momentum, delta P, divided by time, is rate of change of momentum. And there we go. Force net is equal to rate of change of momentum from the impulse formula. A physical quantity that is described as a measure of the resistance of a body to change in motion is called inertia. It's the same as its mass. Okay, 114. Two cars P and Q are moving in a straight line. They have the same momentum. The kinetic energy of Q is greater than the kinetic energy of P. Which one of the following statements regarding the car is correct? Two cars P and Q are moving in a straight line. They have the same momentum. The same momentum. Kinetic energy of Q is greater than the kinetic energy of P. Which one of the following statements regarding the car is correct? Q has a smaller mass than P. Okay. 114. So we're saying they have the same momentum, they have the same mv. The kinetic energy of Q is greater. So that means its speed is greater, therefore its mass must be less. Q's mass is less. Q has a smaller mass than P. Yeah. As I say, I don't know if you guys are there, but how did we work it out? Okay, they're moving in a straight line. This is how I'm thinking. You take two trolleys, a big trolley and a small trolley with a spring in between. You shoot them apart. They have the same momentum, but the big trolley's got a smaller speed because it's got a bigger mass, and the little trolley's got a bigger speed because it's got a smaller mass. So Q, if Q's energy, kinetic energy, if it's going faster, it must be smaller. Q must have a smaller mass than P. Okay, it looks like everybody left the meeting. So I'm just going to quickly finish this off. Where's preview gone? There. I just want to finish off these questions on momentum. And then we're done with it. You can always watch it at home. We did that question. We're just looking for momentum questions now. Okay, ball M moving at speed v to the right collides with a stationary ball N on a smooth surface. Immediately after the collision, ball M comes to a rest and ball N moves to the right with speed v. Okay, that's like Newton's cradle. Both balls must have the same mass for the second ball to come off with the same velocity. Okay, which of the following statements about the collision of the balls is correct? The total momentum is conserved. It's always conserved, folks. And the mass of the balls are unequal. No, I'm looking for one. Total momentum is conserved well, let's read this. Total kinetic energy is conserved, actually is. The masses of the balls are unequal, no. Total momentum and total kinetic energy are conserved, right, and the masses of the balls are equal. Okay, so all three in an elastic collision. I think we're getting to the end. Yay. Okay, two trolleys X and Y of masses M and 2M are held together by a compressed spring between them. Initially, they are stationary on a horizontal floor. Ignore the effects of friction. Okay, when you let them go, Y is going to go slowly, half the speed to the right. M is going to go at, let's say, velocity V to the left. So this is going to be half the velocity because it's got double the mass. The spring is released and falls to the floor while the trolleys move apart. The magnitude of the momentum of trolley X while it moves away is 0, half the magnitude of the momentum, twice the magnitude, the same as the momentum. The momentum is conserved, folks. The answer is D. It started with no momentum, then if that gets momentum X, or let's use a different word, momentum M that to the right, this must have that momentum M to the left to keep this one, which is positive, and that one, which is negative, whichever direction. The two momentums have got to cancel each other out. So they have the same as the magnitude of the momentum of Y. Okay, they've got different signs because they're vector quantities. One momentum would be minus M, the other would be plus M. Okay, an object is dropped from rest and after falling a distance x, its momentum is P. Ignore the effects of air friction. The momentum of the object after it has fallen a distance 2x is, okay, so if it falls a distance 2x, it's going to have a velocity that is going to be 4 times as big. Comes from the half mv squared. So if it's falling at x, so its velocity is going to be, after it's fallen the distance 2x. Okay, so what formula are we going to use here? Okay, the amount of energy after it's fallen 2x, the amount of energy is going to be doubled. Actually, its energy is doubled because the mgh there, h was x. This is mgh. So its velocity is going to be doubled, I think. So if its velocity is doubled, but that sounds wrong. Because when something is falling, when it's fallen twice the distance, its velocity is definitely increased. I would say it's got to be bigger than, greater. None of these looks greater except D. Now what's that square root of 2p? Now why would they? Okay, so if its height changes, okay, let's suppose it starts from 0 and it falls a distance x. It's got so much mgh. If it falls to twice the distance, it's going to have twice the potential energy lost. That's going to go into kinetic energy. So it's going to go in the first case 1, it had so much kinetic energy. In case 2, well, it had double the kinetic energy because, yeah, it sounds like it's going to have double the kinetic energy. So it's going to have half mv squared. is doubled. I'm beginning to think that that's what the answer could be. So case 1 equals the half m v times v of mv squared. So that is when it's fallen at distance x. Now when it's case 2, I'm saying it's going to have, in case 2, going to have double equals, because it's the mgh is converted into kinetic energy, is going to be double. Okay, so if the kinetic energy is doubled, it's going to be equal to 2 times the half mv squared. So the 2 will cancel out the half, so we've got mv times v. Yeah, there's that v times v. So now case 2 is going to be equal to 2 times the half times m times v times v. So if that is twice as big as that, then the velocities must be, yeah, looking like that one. I'm going to have to think about how we can prove that a little bit more, but it's not going to be, I'm just going to have to think about the mathematical way that one can prove it. It's not going to be double the momentum. Okay, let's just have a look at the next one. Okay, there's the end. All right. Okay, so let's stop sharing.